Want to say a few things to you about the week 3 notes and the lecture slides. So here we go. If we just kind of have a peek at the schedule to orient ourselves as to where we are. We're here on week 3. The topic is arrays in C. I'll make a link live with this video once I finish. There might be more than one video. We'll see how it goes. The notes are your primary way to prepare for this, and of course watching the videos. And there is code that accompanies the notes. So I recommend that you type your own code and run all of the programs. I'll prompt you for that as we go along. But it's your responsibility to do this, and you're missing out if you don't actually type the code. You'll learn much faster. You'll become a faster typist. You'll learn the errors and so forth. And of course, there are some tutorials this week. I probably will make videos for each of the tutorials, and it's just to reinforce some of the things I'm going to introduce now. And of course, there's a new problem set, and that's due, next Tuesday. I'll just say a little note here, and I'll mention it again in the future, that these suggested dates are they're soft deadlines. Let's think of them like that. You're strongly encouraged to finish each of these problem sets each week before the next lecture, because we're moving quite quickly. And if you leave completing them until later in the term, you're going to have an awful lot of work to catch up on. And in my experience, students just do much better by keeping up and turning them in each week. That's why we have these suggested deadlines. The ultimate deadline is described on Harper Adams' website for this course. You can find that on the links page on this website if you're interested, and read that document. And from memory, it's much later in the term. It's after early December. Okay, so what we're going to do is I'm actually going to start with the lecture slides, and I usually probably won't do this, but there are a few slides I really like this week, and I thought I'd highlight them. They're not in the notes, so I thought I would do that for you. Okay. All right, so here we go. I'm going to go ahead and turn on my pen because I like to mark it up sometimes. And I'm going to get myself situated before I begin. There we go. One of the concepts that you'll encounter in the problem sets this week is concept of reading levels. What do we mean by reading levels? Well, if there's some text, let's say we're talking about the Dr. Seuss text, one fish, two fish, red fish, blue fish. We all probably have encountered this, possibly. And if we were going to assess the reading level of this text, we might say that it's, year one. It's very simple. When we're just starting to learn language, we can comprehend this, so it might be before grade 1. But, if we're assessing reading level, maybe we could look at some different text. Congratulations. Today is your day. You're off to great places. You're off and away. Well, this has slightly longer sentences. It has slightly bigger words, like with congratulations. So it's probably a little bit further on. And, the science, people who study linguistics would put this around year 3. And then we might look at this one. It was a bright, cold day in April, and the clocks were striking 13. Winston Smith, his chin nuzzled into his breast in an effort to escape the vile wind, slipped quickly through the glass doors of Victory Mansions, though not quickly enough to prevent a swirl of gritty dust from entering along with him. Well, this is a much longer sentence. It's actually 2 sentences, and the sentence structure is much more complex. I hope some of you recognize this writing and the name of the protagonist in this piece of writing, Winston Smith, a very famous novel indeed. Well, the reading level for this piece of writing is grade 10 or year 10. The reading levels is relevant for your assessment because we'll be doing an assessment with some data that categorizes reading levels, and so you'll encounter that concept. So I just mention it here for that reason. Another thing we're going to talk about is cryptography. It's another thing that's going to be touched on in your assessment this week. And what is cryptography? You probably heard of it. It's code and code breaking, and it's a way to hide messages. So we might see something like this that looks just like a jumble of letters. It's nonsensical to English, completely nonsensical to English. Or is it? It may not be, because this is actually a cryptogram, and there's a code. And the code is representing I love C. If I just back up a slide, you can see that there's a one-to-one correspondence of letters for the secret message I love C. And in this case, each letter is just shifted by one letter in the alphabet, plus one. So the I, if I just go back once more, becomes J. Love, L becomes N, O becomes P, and so forth. So this is amongst the simplest kind of cryptography message that you can have. But we want to think about this algorithmically. If we know the secret to the code, we can start to think in terms of our metaphor here of, we have some input and we want to come out with some output, and something happens in the middle. And we'll be working on that this week. What I want to say on this slide, though, is that we have used this model. We've talked about it a number of times in the notes and in the tutorials. And we want to use this model now for the process of taking code that you or I might write in the language C or Python or R. And we want to do something to it in the box with a tool called a compiler. Now, source code is interesting because the computer of itself cannot make any sense whatsoever of the source code that makes sense to you or me in a computer programming language. And we want to use this as an input, subject it to a compiler, and output it to something that computers, can interpret. So we're starting with our input, our source code that looks like this for our Hello World program, and we want to end up with something like this that's in binary or machine code. And that entire program, this is the actual machine code for the program Hello World in C by one compiler, and it's actually longer than this. You can see there's more, and it's in blocks of bits. It's in blocks of bytes, and it creates the instructions that the computer can understand. Okay, so we're going to sort of talk about this for a second. The way we're using our program up to now is we're writing a file. In this case, the file would be called hello.c, and we're using the command in the terminal of make, and we're using as an argument to that command hello, not hello.c, but hello. We talked about this in a past lecture in the notes. And then if we want to run the program, we type ./hello, and it executes the program and executes the instructions. Well, we're going to unpack this a little bit and explain a little bit more what's going on. This make command has been provided to you for simplicity, to just make it as easy as possible to run your first program. But actually there's something else going on. We're actually using a tool called Clang, or it stands for C language. And an equivalent command to make hello and hello is, and you can try this in the terminal. I'm not going to demonstrate it at the moment, but you can actually type this in the sandbox or in one of the repos for the assessments. You can actually type clang hello.c, and what you'll see in the environment is this will result not in a neat executable file called hello like make does, but instead it will create a file, no matter what the name of your input file, called a.out. And you will be able to see this if you do this experiment, and I encourage you to do so. And then we run that the same old way that we run anyone. Now this is kind of a archaic way of doing things. We have this random way of naming every output a.out, and it's a bit old-fashioned, and that's why we've provided make to you. But you know, actually we can we can modify our use of clang with arguments at the command line. And by arguments, what I mean is we have already encountered these if you look at last week's tutorials, but the arguments are modifiers to some kind of command like clang. And in this case, what these modifiers do is we say clang, we want to output a file called hello when we input the file hello.c. And then what we would get in our environment is, for some reason my pen has stopped working. Oh, this is so buggy. Never mind, there it is. We would get the file hello because we told clang with the argument. Sometimes we call this kind of argument the dash, and maybe a letter. It's shorthand for an argument that's specific to a tool that we use on the command line. Sometimes they're called flags that people use. There are different names for them, but they're modifiers. They're arguments to some command. So here, you know, this is a bit nicer. But, you know, this is a lot harder to type. It takes more time to type this stuff than it does to type make hello. And so, again, for your convenience, we haven't done that. All right, so, you know, we've got this basic program here. Let's start thinking a little bit more deeply about what's happening when we compile the program. You know, what clang is doing for us. So here we have our main program definition, int main void, and we have a function, printf, that's printing hello world with a carriage return, new line character, \n. And up here, the function printf, as you know, is located in the standard IO library, stdio.h. So we have to use the #include declaration at the very top of our program to let the compiler know, and now we're going to talk through this process, to let the compiler know that it needs to read the file represented by standard.io.h, and it needs to specifically read out the function printf. Okay, so all this stuff we've kind of taken for granted, and you know, every time we want to use a function, any function, and remember, functions are things that just do work for us. Functions are part of that metaphor, that box where we put some input into the function. You know, in this case, this is the input, the string hello world \n, and we want to get an output. You know, every time we use a function that does work, we have two choices. We either have to use a function that someone else has written for us, and in which case we would usually include the header file that contains the code for that function, or we have to write the function ourselves. They're both very common. It's not a preference over one or the other, but why would you write a function redundantly if one already exists? So, another example is one that we've already encountered is some of the functions that are specific to CS50.h. And it's just again, a convenience. So here we've defined a variable string. We've called the string name, and we've used the function getString to prompt the user for input at the command line. And in order to get the function getString, we have to name the CS50.h header. Okay. So now we also have to link different files. If we use something outside of the standard C libraries, standard.io.h being one of them, we would have to, at the command line, we would have to let Clang know we were doing that by including a different header than the standard library. So in this case, we might modify at the command line. And again, I encourage you to just try this out in the sandbox. We might type Clang output hello, input hello.c, and then link CS50, the name of our header. And, then it will work just as it did with the make function. Okay, so up to now, I've been using this term, compiling, and I've just been kind of slopping it around. But we're going to get more specific with it. The process of compiling actually consists of 4 steps technically. The first one is pre-processing. And, what do we mean by pre-processing? Well, we're talking about including the standard IO.h library. This is one of the programs that we, if you ran the code and went through the notes last week, you would have probably run this, where we declare a new user-defined function called meow. And then we have to define what meow is down at the end of our program. Kind of what this step does. We actually don't have to do this technically. What we could do is we could put the definition for meow right up here in the top, and we could do away with this. But if you have more than one, if you have more than one function, this starts to get problematic. And so by convention, we declare every user-defined function right up at the top like that. And of course, we also have to have standard IO.h, because we have the printf function we're calling in our custom function meow. Now, here's that simple program that we just looked at. We've got getString, and for the getString function, we're calling in the CS50. We've got printf, we've got standard IO. When we include these, pre-processing is such that it goes and finds that file, which has to be available in the system when you installed your programming language, and it pulls out the function that you invoke from it. It pre-processes the code that's needed, that you're using. You're telling the compiler that you're using it. So that's what's happening there. And it pulls it out like that, and it also pulls out a set of rules for the arguments that are required here. Some string that is the prompt. And likewise for standard IO, the pre-processing step would look inside the file and pull out the function definition for printf, right in the very beginning. And it's then that we go through the process of compiling. And what's going to happen there? Well, this code that we've just been looking at gets, once it's been pre-processed, notice up here that now we've got the actual function declarations and definitions. What happens then is that we need to translate this to a language that the computer can understand, not just the code for us weak humans. And this is called assembly language. Now this looks pretty darn ugly. It looks ugly to me too. I'm not an assembly programmer, but there are some people in the dark arts of programming that love looking at this stuff, and we would refer to this as a lower level language. And there are some reasons to dive into assembly language and directly edit it, but for the likes of other kinds of coders, like data scientists, like statisticians, like, other people in other fields that use scripting languages, we would never in a million years look at this stuff. There are a few interesting things I'll just point out here, though. Even though this looks like a lot of gibberish, we can see some organization. We can see a section called main, which is perhaps, let's say, one of the parts of the structure of our program when we declare the body with main, naming it main. And if we look a little bit further down, we can find some parts that we might recognize. For example, if you look hard, you can pick out this get string and this printf. So there are some calls. Here we're getting this indication that something is happening, and it's pulling out the function names. So we can make some sense of this. There are lots of these commands. They all have little arguments, and it's not immediately apparent unless you dive into this. I mean, the good part of this is that we don't have to worry about it. I mean, this class, this is the last time we'll see it in this class. Yet, you'll have a lot of insight just being aware that something is happening under the bonnet here. And that something is very specific. It's not magic. And this is what it is, machine language. Now, once we get the machine language, we do a step called assembly. And the assembly essentially takes the machine language and converts it to binary that the computer can understand. So the binary, is bits. And this is that program that we just looked at. And you can see down at the bottom that there's more to it. Whoops. The ... And then finally there's linking, where remember we've got the header files. In this case there are two, and then we've got the definition of our main program. And what this means with the structure of this particular program, modest as it is that there actually are 3 files involved, all of which need to be translated and processed. And the way that is that they each are handled separately. They're each converted to binary code, and then they're linked together. And this is a simplification of it, where they're just concatenated. Concatenation just means that you add the next one after the first one ends, and so forth. And that's what the process of linking actually does. And really, we still, in normal language, refer to the whole process as compiling, and it just benefits you a little bit to know that there's more going on than just compiling. Now, if we have compiling, it raises the idea, if you think a little bit about it, if we end up with a binary file, it is possible to look in a binary file. I don't know if any of you ever tried that. What typically happens, at least on many modern computing systems, if you open a so-called executable file, you might expect, given what I said, that you would see it. This is just an aside. It's an extra little complication I can't help myself to explain. But if you did open an executable file with Notepad, you'd want it to be a very small file if you tried that, and not a big one. But if you did open it up, you might expect, given what I said, to see a bunch of ones and zeros. But you wouldn't. You'd actually see more characters than that, and some weird characters and letters and spaces and other weird stuff in there. And that's hexadecimal, which is another thing entirely, but it's derived from ones and zeros. Well, back to the topic here. If if we have compiling and we end up with some form of executable in a code format that's all linked together, whether it's binary or hex, we could potentially reverse engineer or decompile that program to get back to the source code. In fact, I already said it, but this is called reverse engineering for software, and it's kind of a sometimes it's practical. There could be some good, legitimate business reasons to do it. For example, if you have legacy code that's very old and been running for a long time, and you've been relying on it for some service, and the code's not very long, you might want to update it, modernize it, make it faster, add functionality to it, and maybe you've lost the original source code. Maybe it's been many years, and you could reverse engineer something to reclaim the original instructions to improve it or change it. Another reason is you might want to have a peek into the intellectual property of a competitor. You'd start with this code. Now, this is very simple, and this kind of process of reverse engineering is very, very much easier with a short program. But you can imagine something like, Adobe Acrobat, or, a web application, or something that is much more complicated, Microsoft Word or what have you, Photoshop. This would be almost impossible. And also, I want to say as an aside that there's some ambiguity in the decompilation process, in that binary code loses some of the nuance that's present in an actual source code. Remember, binary would come out of any starting source code. Could be C, could be C++, C#, Python, Fortran, Fortran 77, Fortran 90. Any of those languages would result in this. And you may or may not know what program you started with. And so figuring out, for example, what kind of loop was used where and how it is specified in the binary you're looking at as opposed to every other code. These are ambiguities in the decompilation process, and it's why many people release the executable. At least the tradition for many decades now has been to go ahead and release the executable. It contains the hex or binary code. It could theoretically be reverse engineered, but practically it's impossible most of the time for some of the program to get back the full functionality because of that ambiguity that's in there. All right, we're going to talk about debugging. What is debugging? Well, it's the it's the process of going through your code and finding errors and fixing those errors. There's a little problem in your code. You debug it by finding the problem and fixing it. In other words, there's a bug in your code. You find a bug and you squash the bug or you remove the bug. Who is this lady? Has anybody ever seen this picture before? Probably not. This lady in a U.S. military outfit is Dr. Grace Hopper. And she worked at Yale University as a researcher. She's actually very high ranking in the U.S. Navy, Rear Admiral, which is very high up indeed. And she, in her time, was a famous computer scientist. And she worked at Yale on the East Coast of America. It's one of the really, really good universities in America. It's on the same par as Oxford and Cambridge in England, and Harvard and MIT and Stanford in the United States. And while she was at Yale, Yale is actually close to Harvard University. She worked on this early computer. This was probably in the 1960s, late 50s, around then. And this is what we called back then a mainframe computer. These days, the power in this computer, I'm not exaggerating. I believe that a computer like this would have about the same computing power as a top-of-the-line modern smartphone. Maybe less than a modern smartphone. This was an IBM mainframe computer. Grace Hopper worked on it. This is a picture of the Mark I So the earliest one of this giant mainframe that was the early basis for computing in, banking and finance, and it was just one of the early computers, and researchers worked on it as well at the university. Well, the term debugging, this is my favorite story. I just love it so much. It comes from Grace Hopper. This is notes from Grace Hopper's notebook. This one's actually from the Mark II IBM mainframe. And there was an error, and she tracked down, her job was as a research engineer working on this mainframe, and there was something going wrong in the computation. And she literally went into the computer and found a physical insect and referred to it as the first actual case of finding a bug. And I just love it. So there was a moth. You can just about tell that this was a moth. She taped it into her notebook, and it was found in one of the relay switches in the program. Just spectacular. I'm going to pause this video here, and I'll probably restart another video. I think this one's long enough. So that's all I have to say about that, and I'll see you in another video.